Sorry, let's get this thing where we want it. There you go. Measurements and density. So today we'll talk about the different measurements that we take in class, and also how to solve for density using those measurements. First off, the SI units. You've probably seen these before, but there are 7 base SI units, and they're not necessarily put order of importance, but length is probably the one that we use mostly in all science. Length and mass you see a lot in a lot of different situations, but the length is meters, mass is kilograms. Probably the third one that you probably see the most is time, and that's measured in seconds. Temperature is Kelvin. In temperature we'll use a lot with gases and in thermodynamics. Amount of substance, the mole, is used in stoichiometry, and you'll become familiar with moles. But those top 5 are probably the SI units that you'll see a lot. The bottom 2, luminous intensity and electric current, the candela and the ampere, more physics related. Luminous intensity is how bright light is, and electric current is how fast electrons move. So you can see that these two are used more in physics. So take physics and you'll learn more about those. But those top 5, meter, kilogram, second, and then mole and Kelvin are the big ones that we'll discuss today, and those are the ones that actually we'll just discuss some of those today, and then the other ones will come up when we get to those subjects. So length is the meter. All measurements of length can be expressed in meters. We can convert to get there. For very large and small lengths, we'll use the SI prefixes. For the metric system, we will talk about the metric system at a later date and how to do those. Movement of the decimal to do those changes to get to the right units. But right now, meter is the basic unit. The space occupied by a sample of matter is called the volume. To calculate volume, we just take length times width times height, and the unit then is thus derived from the units of length. So volume and length kind of go hand in hand. We talk about volume, we're talking about units of length, usually cubed. The SI unit is based on, since the unit of length is a meter, we use the SI unit for volume as meters times meters times meters, which is meters cubed. Obviously, that's a large object, and most volumes we deal with in lab will be smaller than that. So we kind of compromise and use the liter a lot as our base unit for volume. It's not SI, but it's more manageable. Usually it's a 10 by 10 by 10 centimeter object, or 1,000 centimeters cubed would be a liter. Something smaller than a liter would be a milliliter, and it's 1/1000th of a liter, and that means that there's 1,000 milliliters in a liter. The good news is that a milliliter and a cubic centimeter are the same thing, so we can use that interchangeably, and we can get from cubic centimeters to liters pretty fast that way if we need to. So milliliter and cubic centimeter are interchangeable when we talk about their values. But just understand liters are what we deal with the most, but you may see milliliters or cubic centimeters also in volume. Here's an idea of size. The amount of liquid in a dropper full is about a milliliter, and half of a jug of pop or a small bottle of pop would be a liter of that. And you don't find a lot of liter bottles at the store, but you do find 2 liters. So think about half what you get in a 2 liter. That's the difference between the sizes. We can measure volumes in a lot of different things. Graduate cylinders, a volumetric flask in lab, pipettes and burettes, you probably use those in biology, and then syringes are used in the medical field to come up with volume. Now, volume will change with temperature. I mean, as things get hotter, their volume tends to increase because the particles will move faster. So usually when we talk about the calibration of these devices, graduated cylinders, etc., we will usually use 20 degrees Celsius, which is what we call normal room temperature. Obviously, if you've been in some of the classrooms in WSOI, you see that that's not necessarily the case, but 20 degrees Celsius is about normal room temperature. Here are the relationships between these units. A liter is the base unit. Again, that's usually what we hang our hat on. A milliliter is 1,000 liters. And then a cubic centimeter is the same as a milliliter. And so you can compare those volumes. You can say that a cubic centimeter is a cube of sugar, while a milliliter is 20 drops of water. And so 20 drops of water and a cube of sugar are very similar in volume. And then you got microliters, which comes up maybe once in the blue moon, but That's really, really small. And again, that's the volume of a single crystal of table salt. But again, liters is what we use a lot of, and then milliliters and cubic centimeters come up again and again too. Mass, when we use mass, kilogram is the SI unit of mass, but a kilogram is so large that usually when we deal with kilograms, we don't use that a lot. Usually the math that we do and the things that we do in lab are all grams. So 1 gram is 1/1000th of a kilogram, which means if there's 1 kilogram, there's 1,000 grams. That's a conversion you need to memorize. Now, how the gram is derived, it's the mass of 1 cubic centimeter of water at 4 degrees Celsius. Okay, and then obviously the kilogram is defined as a 1,000 grams, as a 10 centimeters by 10 centimeters by 10 centimeter cube of water, having a volume of 1 liter. But that's how it was derived. But kilograms and grams, the two big mass units that we use. But there also are milligrams and micrograms that will come up sometimes during things that we talk about in class. So a textbook's about a kilogram, a dollar bill is about a gram, 10 grains of salt, if you ever counted those out in mass, it'd be about a milligram, and then a single particle of baking powder would be a microgram. And you can see that a microgram is 10 to the 6th, so 1,000,000 micrograms in 1 gram is how that works out. So again, this is the relationship, and there's examples, but kilogram and gram, the two big ones. Gram we use a whole lot, but be able to convert amongst those, that's important. The relationship between mass and volume will tell you if objects will sink or float. We call that density. So density is essentially an equation of mass divided by volume. And this is an equation you'll need to know. We'll do some math with that here this week. When mass is measured in grams and volume in cubic centimeters, we're essentially taking grams divided by cubic centimeters. So our units are grams per cubic centimeter. But the SI unit of density uses kilograms and cubic meters. Again, this is such a large object that uses kilograms and cubic meters that the stuff we use in lab, the number would be so small that the math would be incredibly difficult and not fun with all the decimals. But when we use grams per cubic centimeter for density, things are a little bit easier. So you will see this unit more for density than the actual SI unit, at least in lab and in homework. Now, if we want to compare the density of 4 substances, we got lithium, water, aluminum, and lead. Things to understand is that here we have 10 grams of each, but 10 grams of lithium takes up almost twice as much space as 10 grams of water. And that's just, when you stuff them all together, that's what happens. So as you can see, aluminum takes up less space, and then 10 grams of lead takes up very little space. So when you take the same amount of mass and put it in a smaller space, you get increasing density. Now this last answer here, 0.88, is off. I just noticed that as I was going through this. 10 divided by 0.88 should be 11.4 grams per cubic centimeter. So you can see that increases density as we go across. Okay, as mass stays constant, volume gets smaller, density increases. Mass divided by volume gives you density. So density itself is intensive because it depends only on the composition, not the size of the sample. You could have 100 pounds of gold and 10 pounds of gold, and they both will have the same density as long as it's pure gold. Now, what floats, what doesn't float? So we got corn oil, water, and corn syrup, and we mix them all together, and it will separate out. You may have done this sometime in your elementary school years with that in food coloring. But the big thing to understand is that corn oil is on top because corn oil has the lowest density. Water's in the middle because it has the middle density, and corn syrup's on the bottom because it's the most dense. So if you want something to float on water, it has to have a density of less than that of water. And if you want something to sink in water, it's got to have a density greater than that of water. That's why things sink. That's why things float. Densities of common materials. Just some things to point out when you look at this. You can see that on the left-hand side, solids and liquids have pretty high densities, while gases themselves are pretty low. Chlorine is probably the densest of the gases, and chlorine is a little more dense than aluminum, which people don't necessarily think that when they think about gas versus a metal, but it's true. But then you can see here that gold, mercury, lead, those items too have a lot more density than your typical gases here. What happens to the density of a substance as its temperature increases? Well, the volume of most substances increases as the temperature increases, while the mass remains the same. So when we have something, we heat it up, the volume increases, and then the mass stays constant. So if we heat something up, the density will decrease slightly, which will change. And the only thing that doesn't do that is water, and we'll talk about water, and you'll see why that happens then too. So that's our talk about density and measurement. If you have any questions, please let me know.